I'm Parsa Mirhaji, Director of Center for Health Data Innovations. I'm going to talk a little bit about our perspective from a large healthcare systems view, not the technology view, and my colleague Jans will probably go much deeper into the technology. So in order to understand my presentation, you should really think about a hospital system that covers 1.5 million patients, is responsible for their entire risk. If the patient gets better, we get paid. If they get better, we don't get paid. And we run 14 hospitals. Almost everything that a modern medical system would do, we do at Bronx. The second thing that you should do in order to understand my presentation is to ignore that little crumbled logo up there. It wasn't intentional. I don't know what happened between transition from Mac to Windows. It got corrupted. So ignore that. So you'll be fine. So with that said, you probably know healthcare is a sector of economy that lags. Should I stay closer? I'm loud. That lags really behind all other sectors of economy in adoption of all technology, including modern information technology. There is a real, and everybody is talking about precision medicine, evidence-based medicine. I mean, this is what we aspire to become. If you read literature, everybody is talking about medical centers and hospital systems should learn from every single patient encounter. But no one really talks about what it takes to see all of the patients, see all of the variations of the patients, all of clinical trials that are happening, and they're not working when we actually try to use that knowledge in medicine. There's a huge gap between what we want to become and what we are trying to do in medicine. And the pressure is not just from inside, the pressure is also coming from outside. There are regulations that are expecting that we should be able to explain ourselves, rationalize our actions. We can't, quite honestly, because we don't really know how to process the data that we produce. We now buy equipment that are generating a lot more data, and they are more connected than ever. So we can actually access that data now, but we don't really know how to use them. Every thermometer these days produces data. Anything that we put on our patients creates data. We can collect them, we can put them, and we do. We do have data lakes, we do have enterprise data warehouses, but does it translate to a learning healthcare system? That's basically the dilemma that right now healthcare systems are dealing with. And if you think data is bad and data is dirty, you should see healthcare data. Anyway, so that is the chasm. Again, if you really look into a system that runs 14 hospitals, thousands of practices, hundreds of outpatient clinics and ancillary services, radiology, imaging, labs, and so forth, millions of patients, ask yourself, how many different kinds of analytics, machine learning, AI, or traditional statistical models based on the data that we generate, should we create to deal with all of our patients, all of their diseases in personal level and population level, to deal with our operational efficiency, with our administrative problems, with our financial management, with the logistics. Just think about that number. How many models do we need to create? And what is the kind of architecture that we need to bring about to process all of these models and cater it to our clinical teams, our care coordination teams, to our operational teams, and so forth. So have that question also in mind, because that's going to help you understand where we are going with this. But before that, let's take a look at the state of the art. So what is it that is available to us if we go out and, I don't know, start working with Azure or Google Cloud or any GE healthcare? The very first thing that they will ask us to build a data lake, create a single source of data, get all of the data sources that you have, extract and transform and load them, ETL that data into that data lake. Someone left their pen here. And then for every one of those analytics that we want, if you want to build a diagnostic for sepsis or respiratory failure, or if you want to build an imaging kind of algorithm, you need to now ETL your data again from that single source from your data lake, put it in a data mart, which is specific to that analytic, and sometimes it requires other specific hardware as well. So you can run that algorithm, run that machine learning or AI algorithm, and just imagine if you want to do clinical decision support for sepsis, for respiratory failure, multi-organ failure, all of those, you have to create those data marts after data marts, put them in their own environment and run those analytics, which is extremely expensive, not maintainable. The cost of doing the data lake is huge if you want to bring all of your data points in. And the cost of maintaining every single ETL to support every single analytics is really big. And it creates all of these analytic silos. Analytic number 1 has no idea about the learning that has happened in analytic number 4. But they might be related. We know patients that have respiratory failure or have endured sepsis inside the hospital will have much greater risk to come back later and be readmitted. They have much more risk at home when they go, and all of those analytics that deal with patients' readmission, managing patients' outpatient problems should know about what happened inside the hospital. But right now, the technology doesn't really offer that, and it really doesn't matter if parts and pieces of this model is in the cloud. You send some of the information to cloud to do the compute there, or you store. The framework is the same. We create a lot of analytic silos. In fact, everything we know about medicine is a continuum. Everything we eat, everything that we do, our genetics is connected. But the way we think about analytics, the way we think about problem solving, creates these bubbles we call analytic bubble-making machines. And it really doesn't matter what technology you use. We just create bubbles of imaging models, bubbles of clinical decision support, operational efficiency, and so forth. This is not maintainable. From the clinical perspective, it doesn't really work better for the patients. It doesn't solve the problems. Unfortunately, vendors exploit the situation to compartmentalize and fragment medicine even further by creating these little point solutions that have no idea, are the best cancer detection imaging algorithm that has no idea about patient history, that has no idea about patients' genetics, has no idea about what has happened in the past for the patients, or what the patient is taking as medicine. This is really not acceptable, and that is the reason why hospital systems cannot really, as glorious and fantastic shiny objects we are presented with as technology solutions, we can't buy them because they're not useful. They fragment us. They break the problem into smaller pieces that are not maintainable, and they're absolutely extremely expensive. Again, if we want to modernize ourselves, digitize healthcare, transform healthcare, we need thousands of models that are interconnected. We can't buy thousands of point solutions, sign contracts with thousands of vendors. And these days, I mean, cloud absolutely is a very cost-efficient platform, but put yourselves in a hospital system's place where every vendor asks us to send all of your data to my cloud solution so I can run those 2 analytics that I run. Just imagine what happens. I mean, no sane CIO agrees to do that. So what's the solution? What is it that we think as a large healthcare system we should be doing? So we are building a technology, we call it a patient-centered analytic learning machine. So that patient-centeredness, that getting rid of that fragments of models and fragmentations of the perspectives going away and making the patients the focus of our observation is in the name. And it's about learning about everything that we produce, every data point, anything that we learn as part of the process of dealing with patients, either by clinical trials or research, or by own analytic processes that looks into our data, is that learning machine piece that is essentially enabling us to claim that this is also a platform for learning healthcare systems. So how do we do it? I'm not going to really open under the hood and talk about the exact APIs and the service calls. But it's a fair question if you want to ask. Jans and I will stay after this talk to answer some of those questions. But in a very conceptual, high-level perspective, we extract data and load it into a repository, which is a knowledge graph. And we don't transform data in this process. Although we turn everything into a graph, but you can imagine that it is somehow isomorphic to the shape of the data at the source. So no actual semantic transformation happens at the time of extract and load. Although a lot of semantic mapping happens, which I will explain later, that when we consume the data and put it in our semantic graph, we know what the data is, we just don't transform it to any shape through those semantic mappings. But transform only happens just in time when you want to support an analytic. The lighting here is a little bit off. Imagine again in your head that there's a cloud here. So there's, so obviously you have all of the data in that cloud. That is a huge graph. And these transformers understand how to navigate that graph, make a transformation that will give the exact shape of the data that your analytic needs just in time. So you can run multiple analytics at the same time on one set of data with transformation on demand. And we write the results, all of the output of analytics back into that graph. So nothing goes into a data mart that is separate from the actual input data. Input data and the output of every single analytic sits on the same graph. And there is another technology, which is we call Analytic Tapestry, that connects all of them together, makes them discoverable to each other. Imagine the same thing that a motherboard does in a computer system that connects your flash drives to your camera, to your fancy scanner or whatever it is that you connect through USB to your motherboard, and now all applications in your laptop finds and knows that there is a camera, there's a flash drive, there's a scanner, there's a, I don't know, microphone connected to your, and all of them can access and use this. Analytic Tapestry does that, makes all of the analytics discoverable to each other. So when Analytic 4 is trying to see, does this patient have a risk of any kind, it can go to the knowledge graph, see what are our existing risk scores, what analytics computes them, where are they, what are they, and grab them as part of its own input. It enables to provide input to new analytics from output of previous analytics. It also, in machine learning, in our framework, enables transfer learning to understand what is the new, what are the previous architectures that are similar, trying to solve the similar problems to the ones that I want to solve, and basically adopts that architecture and configuration without our data scientists consciously trying to do it. It gives them options that we have seen this problem before. This is how it has been solved in the past. Maybe you just need 25% more work or a different optimization, and the architecture works perfectly. So by now, we have all of the data, all of the analytics, all of the results of those analytics discoverable to each other, and we have a knowledge base, an ontology, if you will, of more than 2.5 million biomedical concepts, their relationships, their relevance to the input data, to the output data in the form of a mashup of ontology, which is based on a simple knowledge organization system. It's a semantic web standard you probably are familiar with. Our AI, deep learning, machine learning pipeline sits on top of the Analytic Tapestry that knows where the data are, what they mean, who generated them, all of those. And our most current piece of technology we are creating now is the distributed learning transfer, which is about multi-institutional, if multiple institutions want to participate in an analytic process, how they can do it without moving the data. So you can actually run the analytics in place and only propagate learning. So that's our architecture. No fragmentation, everything is connected, all of the analytics know about each other, and it supports all of the varieties of data, and it's very inexpensive. Because it's just one system that we maintain. And it connects all of the analytics into, as I mentioned, a tapestry of all of the models. We actually run a lot of social networking algorithms to find similarities between and relationships between models that we generate in the system. I don't have much time, so I'm going to just run very fast. Our core data store, which all of the incoming data sits in, is a cluster of allograph repository. It's a semantic data lake that is powered by a cluster version of allograph. It's a transactionally asset and real time. And we have built all of those other components that are about phenotyping the patients, creating these dynamic registries, running the algorithms, connecting to the EMR, and so forth around that cluster that contains all of those pieces of the puzzle that I just talked about. And we have a roadmap of projects that we have started back in 2017. So this is not a concept. It is a running system. We are halfway through our roadmap. We now have sepsis management systems, respiratory failure management system, patient mortality management systems inside the hospital. Imaging, we do spinal cancer detection, spinal cord compression detection, as well as appointment management through the same system that knows how to deal with imaging, as well as structured data from EMR, CT scans, or texts and narratives from doctors, all through one system, which is interconnected. I'll stop here. Jans, do you know? Okay, so. Okay, so if Jans doesn't want to talk, I guess I'll take questions.
Thank you, Parsa. Yeah, I think it's a wise decision. There's only a minute or so left. So maybe let's take one question from the audience.
Has the legislation for portable health records helped at all in improving the data quality that you get?
No, but it has really created a lot of problems to get the data. Data quality is a moving target, quite honestly. And we are not too hung up. This is my personal opinion, and others may have a different. I'm not too hung up with improving the quality of the data coming out of healthcare systems. We are trying to understand the quality because, as I said, quality of data is a moving target. Something that is really, really bad for clinical decision support is really, really good for creating an epidemiological model or for monitoring and pattern recognition. We have also learned that there are a lot of information in missingness of the data, when there are certain data points missing, it sometimes indicates certain behavior at the bedside. So we have started to use a lot of these analytic methods to represent, characterize, and understand the quality of the data, rather than trying to spend a lot of money to make really, really small improvement in the quality of the data. And some of it is also architecture. The current healthcare systems are not really designed to create quality data for analytics. They're designed to do something that is more focused on billing or regulatory. So by regulation, you're not going to fix that. You have to design a new architecture. So unless we really change the way EMRs are conceptualized and built, or our lab systems report their lab results, which is millions of dollars of investment and maybe a couple of regulatory frames, I don't see that problem going away.